Hello again. This is Dr. Joel Shertok. I'm president of Process Industries Consultants, a chemical engineering consultancy in Newark, Delaware. And we've been reviewing a variety of topics within the chemical process industries. We've discussed the evolution of the CPI, issues in the CPI, technology within the CPI, and safety in the CPI. With this session, I take a little deeper look at some of the more exotic technologies that the CPI is gradually evolving into. A little bit on separations. We all know that the thing that separates a chemical engineer from a chemist is not reactions. Both the chemist deals with chemical reactions and the chemical engineer deals with chemical reactions, although at a different level. What differentiates the chemical engineer from the chemist is everything that happens downstream. Once a chemist makes something, he can use any sort of lab process to separate out what he wants. The efficiency is usually not that important. As long as you get something to analyze, you are successful. For the chemical engineer, he has to take that reaction mixture, purify it, and have something that's saleable, and saleable at a profit, which means you can't be too exotic and your efficiency has to be very, very high in order for you to make any money on what you're making. So we all know about distillation. We all know about solvent extraction. We all know about phase separation. These are standard chemical engineering operations. But there are many operations that are perhaps a little more exotic and perhaps not as familiar to the public. The first one that I always found very interesting is the concept of filtration. When we think of filters, almost all of us think of paper filters. You make coffee in your morning, and you filter out the grounds from the coffee using a paper filter. And there's all sorts of cloth filters and wire mesh filters that chemical engineers will use to separate out a solid product from a liquid result. So nobody thinks too much about filtration. But the reality is, filtration and the making of filters is a very, very interesting part of chemical engineering. The typical filter is not paper because it simply wouldn't last. The typical filter is made from a polymer. And the polymer membrane filters play a very important part in water purification and chemical separation. So what's a polymer filter? So typically, you will start with a polymer. It could be a nitrate. It could be polyether sulfone. It could be polysulfone. In other words, one of the engineering plastics that is pretty robust over a variety of components. But that's a solid, and you basically can extrude that polymer into a film. And we know that. We encounter polymer films all the time. It's wrapping in our grocery stores. It's thin films that we use to protect our windows. You're familiar with that. But those films are impermeable to just about anything. In fact, that's why they work the way they do. You put water on it, it holds it. You put organics on it, it holds it. Nothing goes through. But if we are to make a filter by definition has to let certain things through and keep certain things back. And that is where the formation of a polymer film membrane is so important. And the development of polymer film membrane is part science and part art. It is a triumph of formulation. And technical personnel who become experts in the creation of a porous polymer film are the equivalent of Merlin the magician in The King Arthur Tales. So what one does in making a polymer membrane is you start with your polymer and you dissolve it. Now, since these are engineering polymers, they don't dissolve in water, they don't dissolve in standard stuff. You need some pretty exotic solvents to dissolve the membrane. If you don't dissolve the membrane, if you don't dissolve the polymer, you're really not going to get anywhere. So you take your polymer solution, and the solvents are very, very carefully selected, and you add something called a pore former. What's a pore former? A pore former is a component that is added to a polymer that, when it's exposed to another solvent, will dissolve out. So, you take your polymer, you dissolve it, you add a pore former. I mean, you can just simple mixing operation. You then extrude that molten polymer or that dissolved polymer through a belt, through an extrusion blade, and you put it onto a metal belt, and you get this thin polymer film. Fine. Typically, it's 5 microns thick. Now, at that point, it's pretty useless, right? But what you do is you expose this to typically water or some other solvent. And what the water does, or the solvent does, is it dissolves out the pore former. And now, instead of having a solid polymer film, you now have a film that has holes in it. But the art comes in is, obviously, you can't have any sort of hole, and you can't have any sort of pore former. You are making your membrane to very strict specifications as to how big those holes are. And that's important because the size of the hole is a function of what bacteria or particulate matter can get through. So certain pore formers and processes will give you a 0.2 micron filter, i.e., in other words, nothing smaller, anything larger than 0.2 microns gets retained. Some polymers are 0.45 microns. That means the holes average 0.45 microns, and bacteria larger than 0.45 microns are held back. Making these membranes and finding the right conditions to expose the film to is part art and part science. Science is fine, but a lot of the art is known to people who are very, very skilled in this operation, and they know how to tweak the formulations to get the pores that they want. And of course, once you have the film, you have to treat it so that it becomes hydrophilic. Polymer membranes tend to be hydrophobic. They don't like water. But if you're using them in water applications, you have to have it like water. So typically you do a post-treatment on the polymer film to give you a hydrophilic property. And that can be either done by bathing it in a chemical, exposing it to a plasma, chemically grafting on hydrophilic materials. Again, there's lots of tools open, and knowing what to use and how to use it is definitely an art. The science guides you, but knowing how to tweak things is definitely an art. So that's relatively straightforward. The understanding of how to take a polymer, turn it into a polymer film, and then turn it into a membrane is if not well known, is practiced by people who are knowledgeable in the art, let's say. The problem is if you're making a polymer membrane, it's not absolute. The holes, the pores in the membrane have a distribution. Now, if you're very, very knowledgeable in making your membrane, it has a very narrow distribution. So if you call something a 0.2 micron filter, that's made by standard methodology, it means that there's a distribution of pores. They center around 0.2 micron, but some can be bigger and some can be smaller. And of course, the tighter the distribution, the better off you are. Now, obviously, the pores that are smaller, that's okay. That's going to keep back smaller particles. That may affect your membrane life, but it's not going to let anything through. The ones that are larger than 0.2 microns means that particles larger than 0.2 microns may still go through. So if you are designing a, say, 0.2 micron particle to hold back a certain bacteria, you may have some pores in that membrane that are 0.45 micron and will let that material through. So you're not absolute, which is why the specs on any polymer membrane allow a certain amount of larger bacteria, particles to get through because there's no way of preventing that. You always have to have a distribution. However, the holy grail of membranes or filters is to make something called an absolute filter medium. By absolute, it means if I say it's a 0.2 micron membrane, it means every pore size is 0.2 microns, none smaller, none larger. The 0.2 is absolute. If something is 0.2 or larger, it will not get through. But making this is, how do you do that? You can't use a standard polymer system because by definition you'll get a distribution. But a company called Nucleopore pioneered the creation of an absolute polymer membrane. And how they did that was very interesting. What you do is you take a polymer film, which you start with, you bombard it with alpha particles. In other words, the helium nuclei. When the alpha particles penetrate the film, they weaken the polymer mesh. And then if you chemically treat this polymer mesh with the weakened portions will dissolve. And depending on the time that you expose your membrane to the solution dictates how big the pores are. And you can get extremely reproducible pore sizes if you understand how the weakened areas react to the solution. Now, this is a much more complex process than the standard polymer membrane. You have to find the alpha particles, you have to bombard it the right way, you have to dissolve it the right way, have to wash it the right way, et cetera, et cetera. But personnel, technical people are constantly refining this methodology to the point where you can buy these absolute membranes, although of course they're much more expensive. The problem is, a problem that people are still trying to address, is that, okay, you're bombarding this film. Ideally, you have one alpha particle in a very small area, so that when you dissolve it, you get a uniform size hole. In some cases, because you really can't control where those alpha particles are going, you'll get a portion where two alpha particles will hit the membrane near each other. That's called a doublet. And chances are pretty good that when you dissolve the doublet, instead of getting 2.2 micron particles pore sizes, you may get a pore size that's bigger. So in other words, you're not quite absolute because of the existence of doublets where two alpha particles came near each other, or even triplets where three alpha particles came near each other. And this tends to make an absolute membrane very difficult to achieve. One way to achieve it, of course, is to limit the amount of alpha particles during the bombardment, but that means your porosity is relatively small, which means that your flow rate and pressure drop is high. You'll get a low flow and a high pressure drop, which is not desirable for a filter, unless you have a very specialized application where it's important to have that absolute membrane, and you're willing to pay the price of a high delta P. So that's one very, very interesting aspect of filters. Many of you have heard about reverse osmosis. Reverse osmosis typically uses a polyether sulfone membrane, just like we discussed previously. But this is made in a very special way. And the special way is you basically have two layers in your membrane. The first layer is your standard polymer membrane, basically 0.2 microns, 0.1 microns, whatever. But on top of that membrane is a much, much tighter membrane. We're talking about nanometers, very, very small. And these reverse osmosis units are able to separate out impurities that a normal membrane couldn't do. So if you have water and you wish to purify it, well, there's two ways of doing it. You can use a standard polyether sulfone membrane, or made from an acetate, and that will hold back most particles. And of course, you'll have to clean the membrane occasionally because it gets all jammed up. In a reverse osmosis membrane, you can, through the application of high pressure, create a very, very pure product at the price of getting a high destructive rejects. So typically, if you put 1 gallon of water through a reverse osmosis membrane, you'll get 60% through of extremely pure water, because the reverse osmosis membrane can even take out salt and minerals. The price is you'll get a 35% concentrated stream that's pretty contaminated. Now, it's conservation of mass. You just can't, you have to do something with the stuff you're ejecting. So for applications where you can't use ion exchange, or you can't use a regular membrane, reverse osmosis is a way to get you very pure water, although at the price of high energy use and a reject stream that's concentrated in nasties. Other methodologies that are being used for separation is simple chromatography. All of us have used chromatography columns to do purification. And basically, the medium in a chromatography column is an inert particle, usually silica gel. And the silica gel is coated with a special material that has a differential solubility for the material you're analyzing for. So that as you inject the sample, and the sample contains many components, each component will have a different solubility in the active layer, the active layer on the inert silica gel. And over a period of a long column, because of this differential solubility, the different components will separate out. Those with more solubility will come out first. Those with less solubility come out later, depending on how you design your column. And you'll get peaks separating as you do your operations. This can be applied in a much larger scale. We're used to seeing, very, very tiny columns, maybe 6, 7 feet, and very, very narrow, that are designed for analytical work. But now, for drug applications, chromatography columns are made large, so actually you can do, I wouldn't call them industrial size, because drug companies by definition are not industrial sized, but you can get practical amounts of purified material through this chromatography column to get an extremely pure final product. And this is a much more exotic form of separation, and this requires a particular expertise that is not common within the outside world. There are people who specialized in these chromatographic separations. And last but not least, we discussed in the previous podcast the concept of ion exchange. And an ion exchange resin, which was pioneered by both Dow Chemical and Roman Haas, by a man named Robert Kunin, the father of modern ion exchange, is nothing more than a polymer, hollow polymer material with pores that has been treated to exchange ions. It usually contains sodium or potassium ions that are loosely bound onto the ion exchange resin. And when the ion exchange resin is exposed to water that contains calcium and magnesium, which makes for hard water, the ion exchange resin, as implies by the name, will exchange. It will release its sodium and release its potassium ions and grab onto the calcium and magnesium ions, so that the water coming out of the ion exchange resin is softened, i.e., the calcium and magnesium that cause soap to be scummy and cause deposits is held onto the ion exchange resin, and in its place, the water now has sodium and potassium ions, which are much more benign. They're infinitely soluble, so that they never played out, and it's great for washing your hair, and it's great for shaving. But it is possible to customize ion exchange resin so that you can get all sorts of performance. You can get all sorts of rejections. You can get all sorts of properties to customize your ion exchange resin for a particular application that you need. And again, people who do this are wizards. They understand what treatment is needed to make an ion exchange resin work in a certain way. Bob Kunin was an authority. He wrote several books on ion exchange, and he could whip up an ion exchange resin to do pretty much whatever he wanted it to do. One note, the true author of ion exchange is not Bob Coonan, but it's Moses of biblical fame. There is a passage in the Chumash, in Exodus, where the children of Israel need water, they're thirsty, but the water they come to is brackish, contains high concentrations of salt. It's not drinkable. And the passage says that Moses takes a certain tree and throws it into the brackish water, and the water becomes drinkable. And of course, the children of Israel, not having a background in ion exchange, thought this was miraculous. And Moses didn't know much about ion exchange either, but through folk wisdom, they had learned that certain trees, through a mechanism they had no idea, they couldn't understand, had the ability to turn brackish water sweet, and did it by ion exchange. For some reason, this tree had loosely bound sodium and potassium ions that were able to exchange for the brackish materials in the water. So ion exchange probably has the longest antecedents, say about 3,000 years, of any exchange system in the chemical process industries. So this completes the concept of exotic separations methods. There are more coming every day. When I was in Princeton, one of the professors there pioneered something called parametric pumping. And that involved doing rapid changes of, say, pH, back up and down, up and down, up and down, which would essentially simulate what a distillation column does. It basically imposed changes on the concentration of material going through by rapidly changing pH, and over a series of pH changes, actually was able to concentrate the product of interest. Never quite got off the ground, but I understand that it's being kind of revived because it's a low energy way of getting separations, and therefore very, very consistent with the green engineering of today. Again, Dr. Joel Shertok, Process Industries Consultants, thank you very much.